Okay. Welcome to Math 150. This is multivariable calculus. And so I guess every time the pen dies, it goes to huge thickness. Right, so what I want to do today is I want to talk briefly about vectors. I think you've all seen vectors before, so I'm not going to do too much. So we're used to doing things in the standard coordinate axes. Here's the x direction, here's the y direction. We can write some vector v as its x component and its y component. Maybe I move over 2 units and up 3 units, and this would give me the vector 2, 3. And so one way to write this is it's x times the vector 1, 0 plus y times the vector 0, 1. And so the vectors in the direction of the coordinate axes are very special. So we have the coordinate axis unit vectors. So in 2 dimensions, E1 is going to be 1, 0, and E2 is going to be 0, 1. What do you think it would be in 3 dimensions?
E1.
And what would E1 be?
1, 0, 0.
Exactly. And you would have E2.
So on.
Exactly. E3 would be 0, 0, 1. We also use I hat for E1, J hat for E2, K hat for E3. A hat means a vector of unit length. So if I give you the vector v equals 3, 4, what would be the length of v? It would be 5. And it's going to be the square root of 3 squared plus 4 squared. So whose theorem is this?
Pythagoras.
Exactly. So this is Pythagorean theorem. And so if I give you some vector, and I can write it as is the x component, here's the y component, and then the hypotenuse is the square root of x squared plus y squared. So this is the Pythagorean theorem in how many dimensions?
2.
So in 2 dimensions, the length of v, is the square root of vx squared plus vy squared. What do you think would be 3 dimensions? Now helpful if we have a vector is vx, vy, vz. What do you think its length would be? Well, you got to be careful because it's got to be so. What's a special vector to look at? If the third component is 0, it should just reduce to something we've already known.
Yeah.
So if you did a cube root, that's not going to reduce nicely.
Just the same thing.
So what would you try?
Square root.
The square root of
Everything squared out.
So vx squared plus vy squared plus vz squared. And there's a nice way to prove this. Unfortunately, I'm not going to have enough picture. So let's say we have some vector here in 3 dimensions, okay? And then I have underneath it, I'm going to write it like this, and I'm going to come up like this, okay? So this is my height. This is going to be my VZ. I'm going to just call this maybe for now R. And so if I draw it like this, I've got a triangle in 3 dimensions. But that triangle is still in a plane. I've got a right angle and I've got 2 sides. So by 2-dimensional Pythagoras, we have the length of V is the square root of R squared plus VZ squared, right? But we can now write R as Vx, Vy, right?
Yeah.
So by two-dimensional Pythagoras, what's the relation between R, Vx, and Vy?
R equals Vx squared, the square root of Vx squared Vy squared.
Right, so I'm going to write it as R squared is Vx squared plus Vy squared. Because if I write it like this, we can just substitute in. And now we get the length of V is the square root of Vx squared plus Vy squared plus Vz squared. So we initially used Pythagoras to get the length of vectors in the plane. It actually turns out to work for vectors in 3 space, and you can generalize this to 4 space and higher. It just gets harder to think about. And the idea is by drawing the vector V as something in the xy plane as one of the vectors and then just going straight up for the other one, we only had to know two-dimensional Pythagoras. And then we kept applying it. Well, we often work in n-dimensional space. If I give you V is V1 dot 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 Vn, then the length of V would be the square root of V1 squared plus Vn squared. Right?
Yeah.
Now we introduced some important notation called the dot product. And we'll see later why it's so useful. But if V equals V1 through Vn, and W equals W1 through Wn, then V dotted with W is V1 W1 plus dot 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 plus Vn Wn, or you can write that as a sum, k goes from 1 to n of Vk Wk. So you basically multiply component by component and then add. So for example, if I gave you V equals 3, 4, and W equals 2, negative 1, what would V dot W be?
Wait, wouldn't that be like 6 minus 4?
Yeah, so it's going to be 3 times 2 plus 4 times negative 1. So 6 minus 4 is 2.
Yeah.
Now here's something that's really nice. V dot V, that's V1 through Vn, dotted with V1 through Vn. So what would you get if you do that dot product?
V1 squared.
Yep.
V2 squared dot 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 Vn squared.
So what goes between the V1 plus? Wait, we've seen this expression before. What is this expression?
So it's not the square root, but
The square of what?
V.
The length of V squared. So the length of V is the square root of V dot V. So this is one use of the dot product, is it allows us to calculate lengths. We will see later there's a big theorem. V dot W equals the length of V times, do you like that? Times the length of W times the cosine of the angle between V and W. So if I give you 2 vectors, here's the vector V, here's the vector W, and here's the angle between them. Well, if I switch the order of V and W, I switch the angle and I make the angle negative. Does the cosine of theta equal the cosine of negative theta?
Yes.
Yeah, So because cosine is even, as cosine is even, order doesn't matter. So we'll see later why this is true. But this is a very useful theorem. And so if I can calculate dot products, I can calculate lengths. I can then calculate the angles between things.
Yeah.
And then the last thing is to make sure we understand how to work with vectors. If I give you your v is 3, 4, 8, and w is 2, -1, 3, and u is 8, 5. What is v plus w?
Isn't that just 5?
Yep, so it's 3 plus 2,
3,
4 minus 1.
and then 11.
Yep, 8 plus 3. So you just add component by component. So it would be 5, 3, 11. What if I gave you 2v? What would that be?
6,
So 2 times 3,
8,
2 times 4,
16.
2 times 8. And so that would just be 6, 8, 16. What about v plus u?
11, 9, 0, E.
So v is the vector 3, 4, 8. And u is the vector 8, 5. Can we add these two?
No.
No. Not add, not same dimensions. So you can't always combine things. Okay?
Yeah.
So the last thing I want to just talk about is, so we have the dot product theorem. So it's here is v, here's w, here's the angle between them, EW, and we're saying v dot w is the length of v times the length of w times the cosine of the angle between them. If I double v to 2v, what happens to the left-hand side?
You what?
If I double v, if I make every component of v twice as big, what happens to the left-hand side?
Twice as
Left-hand side is doubled. What happens to the right-hand side? Does the angle change?
No.
Does the length of w change?
No.
If I double v, what happens to the length of v?
Doubles.
Doubles. Right-hand side doubles. So this formula is reasonable. Whenever you have a formula, you always want to ask, is this reasonable?
Yeah.
And here's a simple test we could do. You think of anything you've seen in trig that has a cosine in it. Where have you seen a cosine? Do you remember any theorems from trig?
Oh, like the two sides.
Yeah. So which
Sine, the sine of 2x.
okay, well that's trig identity. But do you know any theorem that involves cosine?
Probably.
So think, what kind of different laws did you have in trig?
The sine one.
Yeah, the sine one
sine.
and the cosine one. So if I give you a triangle and we had the sides were A, B, and C, and the angles were A, B, and C, the law of cosines. So it was C squared
equals A squared plus B squared minus 2 AB cosine C.
cosine C.
What should that be? Big
Oh, that
C?
should be big C, that's right. And so what's really going on is it's the law of cosines that drives the dot product theorem. And so this is the last thing we're going to do, and then we're going to call it a day. So I'm going to do dot product theorem in 2 dimensions. The proof in general is pretty simple. So let's write V as V1, V2. Sometimes we do Vx, Vy, sometimes we do V1, V2. I'm doing V1, V2 because this will generalize better to higher dimensions. And then we do W, would be W1, W2. If we had 3 dimensions, what would we have?
V1, V2, V3.
Exactly. So what is the length of V squared?
V1 squared V plus V2 squared.
And the length of W squared.
Same thing, just with the
And then that's 2. And then what is
it 2?
Yeah, V1, I'm sorry, what is V dot W?
V1 V1 W1
Good,
plus V2 W2.
good. And so now we want to compare V dot W to the length of V, length of W, cosine theta VW. Let's square both sides. So V dot W squared versus V squared, W squared, cosine squared times the angle. So this is going to be V1 W1 plus V2 W2 versus V1 squared plus V2 squared, W1 squared plus W2 squared, cosine squared. Okay?
Yeah.
And so if we think about what's going on, here's V, here's W, here's my angle between them,
Mm-hmm.
and we want to show that these 2 sides are equal. Oops, this should be squared over here. Okay?
Yeah.
So the question is, how do we handle the cosine squared term?
Isolated.
So do you know any other way to write cosine squared that might be helpful? How else could you write cosine squared?
1 plus.
Not 1 plus, 1 minus.
1 minus, sorry.
So cosine squared theta equals what? 1 minus
Sine squared.
sine squared theta. So maybe sine squared is going to be easier. So if we think about this triangle, if I draw this line over here,
Mm-hmm.
if this is the length of W, what is the length of the red line?
Perfect.
So what the hypotenuse is the length of W. So what is going to be the length of the red line? Using trig, the hypotenuse is length of W, the angle is theta, or theta VW.
So is that like a right angle?
Yep, so it's
Okay.
coming down to a right angle.
So W, length of W.
Yep.
Over 90. Weird.
You're making it hard. We've got a right triangle. We know the hypotenuse. We know this angle. So what's the sine? What's the length of this side?
That times the cosine angle.
So the cosine of theta times the length of W.
Oh. Why don't you use the law of sines?
No, just use the definition of trig functions. What's the length of this? Whoops, I'm in erase mode. What's the length? You've got a right triangle. You know the hypotenuse. You know the angle. So how do you figure out this length? What are your basic trig functions?
Like Pythagoras.
What are the trig functions? What trig functions do we have?
But
Give me trig functions. What trig functions do we know? Can you use any of these trig
a
functions?
squared plus b squared plus c squared.
That's not a trig function. That's a relation. What's the trig functions?
Like the law of cosine.
Nope, that's a law. What are the trig functions? List trig functions.
Mm,
What are the basic functions in trig?
okay.
Well, you've got some on this page. Look at this page. What are the basic trig functions?
Cosine equals 1 minus the sine squared.
Well, that's a relationship. So what are the functions in the relationship cosine squared equals 1 minus sine squared? What two trig functions do we see?
Cosine and sine.
We see cosine and sine. So what's the definition of cosine?
Opposite over.
So which one is cosine? Is cosine opposite over hypotenuse or adjacent
That's
over?
adjacent.
So cosine is adjacent.
So sine.
So which one is sine?
Opposite over adjacent.
So if I know the hypotenuse and I know the angle, what would this height be?
The sine of the angle.
Of the angle, right?
Yeah.
And so if you want, one way to look at what we have here is if I do W sine theta times the length of V, that's going to be the area of the parallelogram.
Mhm.
And so when I'm writing things out, putting in the sine squared, this is basically going to be giving me an area squared. I then still have to deal with the 1. So we'll stop here and we'll finish the proof of this next time. But I wanted to just stop the proof, give a little bit of a sense of what's going on. We see that the law of cosines is going to come in and make a play. We can see that we can write the cosine squared as a 1 minus sine squared, and we can see geometrically that this is coming in as like the area of the parallelogram. So we need to somehow find ways to interpret the area. We talk about these component by component. We often use I hat, J hat, K hat for the X, Y, Z axes. We use E1, E2, E3. The length of a vector is the sum of the squares of the components. And then the dot product is just multiply component. Theorem is that V dot W is the length of V times the length of W times the cosine of the angle between. All right, so that is a good place to stop for the first lecture. Stop.